Welcome to our thermodynamics video series. This new video is about a problem-solving template and methodology that has worked very well for me over the years. That is generally considered to be a good approach to the types of problems that you're most likely to have to solve either in thermodynamics or fluid mechanics. And frankly, is just a good step-by-step approach for many engineering types of problems that we are faced every day, both in industry and here at the university. And I suggest that you make it your own. I'm going to ask you to submit your problems using this template this quarter. So typically what happens in an engineering setting is we're given a problem, either word of mouth from someone we work with, or in the case of a class like this, a textbook example that outlines a various series of background information and what we need to find as a result of this for the purpose of analysis. So the methodology in the template consists of first identifying very clearly what is given to us as part of this engineering problem. And so I label this as step number 1 in my template, and bullet point form is sufficient for this purpose at this point. Just list down everything you have from word descriptions of the problem that help to frame exactly what we are looking at, to listing all of the numerical data that's given to us along with the symbols that are used to represent that numerical data. P for pressure, for example, and make sure, for example, in the case of pressure, that you identify whether we're dealing with gauge pressure or absolute pressures, because this are often very crucial small bits of information for many of the models that we'll be using to solve problems. Second is to very clearly identify what is it that we're trying to find as part of this analysis. So usually it's a variable, a property that we don't know yet, or an output of a given process that we're trying to establish. Things like that. It might be multiple step, in which case you would put in bullet form what exactly it is that you're looking for, part A, part B, part C, etc. Third, very important aspect of the problem-solving process is to sketch some of the information that we are given. Could be a sketch of the apparatus itself, could be XY graph of some of the properties that we're looking at. Could be a cycle PV diagram or TS diagram in a course like this would be very appropriate. Things of that nature. Anything that can help us sort of frame the problem as we're seeing it. Again, a big part of this process is to sort of get your mind on a track to the problem solving steps. So far, we really haven't we don't appear to have been doing a whole lot of problem solving. We're simply doing problem organizing, or so it seems. But a big part of problem solving is this problem organizing, as it turns out. After we have our physical sketch of the problem data, as well as any graphical information that we're given in terms of diagrams, etc. Next is to list the assumptions that we are making, the simplifying assumptions and the names of the physical models that we are applying, that we think we will need to apply in solving that problem. Arguably, in my opinion, this is the most important step in the entire process. I say this because it really frames the limitation of the solution that we end up presenting at the end of the day. Later on, if we determine that the tolerance or the accuracy of the solution that we came up with isn't sufficient for whatever purpose we're trying to achieve, we go back to this particular step number 4, the assumptions in the model, and see if we can refine them, relax them somehow, and make them more specific to the problem that we're trying to address, and start from there in terms of solving, refining the problem. Last and finally is the solution itself. Here is where you put pencil to paper and you start to methodically go through the process of solving the problem that you were given in the first place. I strongly advise, it's good practice really, to keep your solution process as much in symbolic form as possible as you move through any given problem. In other words, while it's very tempting to immediately substitute for the values that you have, the numerical values that you're given at the very top of the problem, keep things symbolically. Keep, say, for example, the pressure is P as you go through your analysis, and once you're finally down to the very last few steps, is it appropriate to substitute in for P, whatever P the pressure is, etc. List down what sets of equations you feel are appropriate, that are consistent with the simplifying assumptions that you've made in step 4. Establish all these parameters in step 5 as you go through the problem solving process. We're going to be using this template to give an example problem pretty soon, but there you have it now. Thank you.